Now that we are familiar with covering maps and some of their properties, we can use that to help us compute the fundamental group. So let's briefly recall what the fundamental group is. Definition: let Y be a space. And you can always assume that your space has the properties that we've been assuming up to this point, namely that it's path connected, locally path connected, Hausdorff, those kinds of assumptions. Not necessarily required, but those are the kinds of spaces we usually work with anyway. This also might look a little bit strange because we're calling our space Y instead of X. But the reason for this would be, of course, that Y will play the role of the base and X will play the role of the cover. Let Y be a space and Y0 be some point in your space. So then the fundamental group of Y at Y0, this is by definition, this is the set of all homotopy classes of loops at Y0. And when we say homotopy classes, we are of course referring to path homotopy, but we're just being a little bit sloppy and we just say homotopy. So what this is supposed to represent is that, it's basically going to be a set, and the elements of the set, it would be, let's say, F, and the bracket around it is the homotopy class of A. What is F? So F is a loop at Y0, and this is a loop in Y. So that just means that F is a path, so it's a mapping from 0, 1 into your space. And f of 0 and f of 1 are the same because it's a closed loop, and they're both equal to Y0. So that's what we mean by a loop. And the equivalence class of A will represent not just F, but everything that can be homotoped into F. So let's say this is Y0, and let's say F goes like this. Now, if you slightly were to perturb F, just a little bit slightly homotope it a little bit like this, and this is G, let's say going in the same orientation, then you would simply say that G belongs to the homotopy class of A. You treat these as being equivalent in the fundamental group. However, let's say that instead G was to look a little bit different. Let's say there was some kind of hole over here. That was a hole, and then you had G going around that hole. Then it is intuitively clear that you will be unable to move G to be aligned with F because there's this empty hole in your space, and you somehow have to move across it. So then you would say that G does not belong to the homotopy class of F, and then the homotopy class of G and the homotopy class of F, they're going to be different classes. In fact, they happen to be disjoint classes, but they're going to be different classes. So that's what the fundamental group is. And it's a group, not just a set, because as we've discussed, the way you multiply these classes together is by juxtaposition. So it would just mean that, returning back to this picture, if you were to do F multiplied by G, then the picture here would simply mean you first move along F, and then you move along G. And the way we describe that is by writing F juxtapose G, and it's the class that you form out of that. So this is the fundamental group. And we talked about the problem of how does one calculate the fundamental group of a topological space at a certain point. So let's discuss this. This is what we call the monodromy theorem. Monodromy theorem. So here's how it goes. We're going to assume that X is simply connected. Simply connected means that the fundamental group of X is trivial. Or if you want to put it a different way, it would mean that every loop in X homotopes down to the constant loop. It can be homotope down to a single point. It can be shrunk down to a single point. That's what it means to be simply connected. Intuitively, this is supposed to represent a space that has no holes in it. Because since there's no hole, anytime you have a loop, all of that stuff inside the loop is part of the space, and then you can move through it and collapse everything down to a point. So we assume that X is simply connected, and pi from X to Y is a covering map between two topological spaces. And now we're going to pick some point in Y. It really does not matter which one you pick, because as we've discussed previously, if you choose a different base point and you calculate the fundamental group, the fundamental groups are isomorphic to each other. But it's just that the way the definitions are set up, you're required to pick a base point at which you're going to draw all of your loops from. So that's just the way the definitions are set up. Even though the kind of point you choose for calculating the fundamental group really would not matter. So you pick some point, and then you're going to pick something in the fiber over that point. And you're going to pick x0 in the fiber. So this is what we call the fiber over y0. This is supposed to represent all of the pre-images of this point. That's supposed to be the collection of all elements in X that get mapped to y0. So you pick any one of them. So again, these are sort of like arbitrary choices. These are like your initial conditions that you need to specify in the beginning. And sometimes the notation that we use is we just write x comma x0, y comma y0, like this. And then this is indicating that the covering map, it maps this point to that point. Okay, so here's what the monodromy theorem says. So now it says that let F be a closed loop. So this is a homotopy class of a closed loop at y0. I guess I should have put it in brackets. So this is a homotopy class. So all this means is that F is a map from the interval into Y, and the endpoints get mapped to this point y0. So we're going to denote F tilde to be this is going to be a path in X with F tilde of 0 being equal to x0. So this is the unique lifting of F. So the picture is you have a mapping into Y, which we're calling F, and it maps 0 to y0. And here you have the covering map. And the lifting theorem that we've talked about last time says that if you have a path in the cover, if you have a path in the base, that path can be lifted all the way up to the cover. So you can lift it all the way up to the cover, and we usually denote that as F tilde. So F tilde is the one that lifts. So the diagram commutes. So if you were to do pi, if you were to project it back down to the base, that will give you the original path. But be careful, but its terminal point is not necessarily equal to, so the point in X that projects down to y0, this is the initial condition that we have chosen. This is what we're calling x0. So we're saying that when we lift the path, it satisfies the initial condition that it starts at x0. But the point that it finishes at does not need to be x0. So just because the path in the base is closed does not mean that when you lift it, it lifts to a closed path. So the terminal point is not necessarily equal to x0. Rather, it's something in the fiber over y0. So you would just say it's something that is in the fiber over y0. That's all you can say. It's not necessarily the same point. So what does the theorem say? So the theorem says, so then we have, so this is the monodromy theorem. We have the following relationship, that F is path homotopic to G. So maybe I should say it like this. So we would say that F and G are equal. These are equal in the fundamental group. So F and G represent two closed paths at y0. So when we're saying that these are equal, basically what we're saying is they're homotopic to each other. F and G are homotopic to each other. That's another way of saying that the homotopy class of F and the homotopy class of G are the same. So they're equal in the fundamental group if and only if, and this is the monodromy theorem, if and only if, when you take the terminal point of the lifted path and the terminal point of the other lifted path, they're the same in the covering space. So that's why it's called the monodromy theorem, because everything is determined by what the lifted paths do at just that one single point. That's the only information you need. So this is a review from last time. And in order to calculate the fundamental group, we're going to do this in the case when we have quotients. So we're going to assume that the base space, it arises as a quotient. So let's remove this down. So we will discuss how to compute the fundamental group in the special case of a quotient. So namely, we're going to assume that X is simply connected G, this is going to be some subgroup of automorphisms, is a group that acts evenly on X. And so we have a covering map pi from X to its quotient. So we have a covering map between these two spaces. And we will explain how to compute the fundamental group of the quotient that you get at a certain point, right? At some point, it doesn't really matter which one. But I think it would be helpful to explain what the quotient is, and then to also go over how this map is being defined. So let's just do that review also. The most difficult part of all of this is not forgetting the definitions. Like if you really get these definitions, then most of what we're doing is rather straightforward. So the hardest part is just recalling all of this notation, all of the vocabulary and what it says. That's why we're reviewing again these topics so that hopefully it makes more sense. So here's how this works. So X, so let's do this. So let's pick some element in X. And we're going to denote by A mod G. And another notation that I like to use, which makes it simpler, it's A with a bar on top of it. So this just means class of A. Now be a little bit careful. This is not a homotopy class. That makes no sense. Homotopy classes are for paths. That's not a path, that's a point. So you can call this maybe a mod class. This is a mod class of A. So how is this defined? Well, this is going to be the collection of all elements in your space that can be translated into position A, so that G of X is equal to A for some automorphism. For some automorphism An automorphism is it's sort of like a permutation of X. It's more than a permutation of X because it has to be a homeomorphism on top of it, but that's basically what it is. It's sort of like some kind of permutation of your space. So we often call them translations because that's how we draw them. That's not necessarily how they look like, but we're saying that there's a translation. So basically, yeah, so these are all points that can be translated into A. If you want, you can also rewrite this a little bit differently. You can also solve for X. So you would say that X is equal to G inverse of A. Again, G is a homeomorphism. It has an inverse. So X would be the inverse of A. So you can also say that it is all of the elements that are translations of the A. That's another way you can say it if you want to. And of course, if G is in the automorphism group, then G inverse is in the automorphism group. So if you wanted to, you can actually just remove all of this and you can just call it G. You can just relabel G by G inverse. It's again in the automorphism group. So it would be all, this is basically the translations of A. You take this element A and you move it by using the automorphisms in G, and all of them that you get, you call that the mod class. And then X mod G would then be the set of, let's say, the class of A, where A is in the original space. And then you observe that if you have, let's say, A1 and you have A2, then they end up giving you the same class if and only if one, like A1 and A2, well, you can say that, like, let's say A1 is G of A2 for some G. And you can, of course, move the G over to the other side if you really wanted to. So two elements will generate the same mod class if one is the translate of the other. So that's the way we define X mod G. And how do we topologize this? Let's take this away. How do we topologize this? And we have an obvious map, an obvious map. Some people will call it a natural map. A natural map or an obvious map from the space to its quotient. And it's just, you send an element to its mod class. So pi of A, you take that element and you just send it to its mod class. And we topologize the quotient so that pi is a continuous map. At the moment, pi is not a continuous map. That would make no sense. X is a topological space, but this is just a set of classes. In order for you to talk about continuity, you need to put a topology on this, so then it makes sense and you can talk about continuous maps. So the way we put a topology on it is we have to declare what it means to be open. So we say that U is something that's open in the quotient. Now this is a little bit complicated. So what is U? U is a set of mod classes. So U is technically a set of sets because the elements of the quotient are classes, so those are sets, and U is an open, so it's a subset of the quotient, so it is therefore a set of sets. So rather complicated. So we say that U, so a set of mod classes, is open if and only if, so that's the way we define what it means to be open, if and only if when you pull it back to X, that becomes open in X. And this makes sense because X is a topological space, so we know what it means to be open in a topological space. So that's how we topologize the quotient. So let's say what the main theorem is. So this is the main theorem. Okay, so here's how it goes. We're going to assume that X is simply connected. And G, this is going to be some group of automorphisms. This is a group of automorphism that acts evenly on X. And let's pick some x0 in X. And so if you look at its mod class, that's going to be something in the quotient. So then here's the theorem. So then the fundamental group of the quotient at this point x0, again, the point really does not matter that much. It's just that the way the definitions are set up, we have to use a base point. So then the fundamental group of the quotient is isomorphic to the group G itself. So let's say that again. The fundamental group of the quotient, under these assumptions, the fundamental group of the quotient will end up being isomorphic to the group of automorphisms that was used to generate the quotient. And this nicely illustrates a theme of modern mathematics, where I say the theorems are easy, but the definitions are hard. So that's how modern mathematics operates, that all of the complications are pushed into the definitions, but once you get to the theorems, they're very easy to prove. And a lot of the theorems, the way you prove them is it's the first thing that comes to mind. The first thing that comes to mind is the way you prove it. So there's absolutely nothing clever in proving the theorem. So I'm going to show you how you prove it. I'm going to write out how the isomorphism is being created, and then I will leave that detail for you to check. And as you will see, it's actually fairly simple to check if you happen to get the definitions. So here's the proof. So I'm going to call this proof outline. What I'm going to do is I'm going to construct the isomorphism between those two groups, and you will check on the homework that this is indeed an isomorphism. So here's the proof outline. So we will construct two homomorphisms. For lack of a better name, I'm going to call one of them alpha, and the other one I'm going to call beta, because I'm running out of symbols. So you're going to have a group homomorphism that will take you from this group to G, and then you will have another group homomorphism that will take you to G back to that group, and then you will show that these two homomorphisms are inverses of each other. And then you will show that alpha composed beta and beta composed alpha are inverses. And that would complete the proof. Now, if you understand the definitions very well, then what we're about to do will feel very natural. It will feel very, very natural. So here's how alpha is being constructed. So here's how we do this. Here's what we know. We have X. We have a point in X, x0. We have the quotient space. We have the quotient map pi. And then we have x0 bar, which is the mod class. So we have a covering space. Now, let's say let F be a homotopy class in the quotient space. And the question is, how do you define alpha on this homotopy class? So what is it? And whatever it is, it has to end up in G. So you see that? In order to define this mapping alpha, you have to pick something in here. And by definition, these are homotopy classes of loops. And you have to define how you're sending this loop so that it ends up in the automorphism group. So what do we know about f? Well, f is a closed loop. So it's a path in the quotient that has the initial condition that f of 0 is equal to f of 1, and they're both equal to x0 bar. So you therefore have a path, so you have a mapping from 0, 1 into the quotient, and we're calling this f. And it maps 0, that's the initial condition, it maps 0 to x to the class of x0. Now it also happens to map the endpoint, it also happens to map 1 to x0 as well. But that's not the initial condition anymore. So now lift f to f tilde. So this is going to be a path in the cover that will satisfy the initial condition that f of 0 is equal to x0. So by the lifting property, this path lifts into the cover. So now we lift it into the cover f tilde. And the proof of this theorem is motivated by the monodromy theorem, that everything is determined by the terminal point. Okay? So then, if you look at the endpoint of f of 1, so this is f tilde, the lifted path of 1, it's not necessarily equal to x0 again, but it's something in the fiber. So that's going to be in the fiber of x0 bar, which is just another way of saying, yeah, I mean that it's just in the fiber. That's just another way of saying that it's, yeah, that's just another way of saying x0 bar. I know this looks very strange. Maybe I should not write this. You see, the reason why this looks very funny is because you're thinking of this as a point, but it's not. But a point happens to be a set, so whatever it is, it's in there. Based on our notation, this is the fiber over x0 bar. But the fiber over x0 bar happens to be x0 itself. Not that it really matters, but maybe I should just keep it like that, not to overcomplicate this. So we're still constructing this map alpha. So this is inspired by the monodromy theorem. You lift your path, you lift your loop, and you look at the endpoint. The endpoint is going to be in the fiber over x0. But how do you get an automorphism of this? So let's say, okay, so let's do this. So let's say that f tilde of 1, well, it's something. I think maybe this will make it easier. Okay, let me take, I'm trying to make this a little bit easier. So here's what I mean. F tilde of 1, let's say it's equal to x1. And whatever that is in our cover space, x. So then the mod class of x and the mod class of x0 are the same because they're in the same fiber. Because of this, by definition, hence, there is a unique there's a unique automorphism of your space that will translate x0 into x1. So maybe this picture will make it a little bit easier. So let's go back to this picture. The lifted path, its endpoint, is not necessarily x0 again. It's not necessarily a closed path. So so it's a path from x0, and let's say the other path is x1. So then x0 and x1, they are in the fiber over this point. And so by definition, it means that they are related to each other by something in the group. There's something in the group that will translate x0 into x1. There's something in the group that will do that for you. The reason why it has to be unique, yeah, and it has to be unique. There's exactly one. I mean, I'm going to leave that for you to think about. It basically has to do with the fact that you have bijections. There's a unique automorphism that will take x0 to x1. And that's how you construct. We define the alpha map to be this group automorphism. So that's how the alpha map is being created. Okay, that's how you find it. Okay, so let's maybe go through this again. In order to define alpha, you pick something in the fundamental group. So what is this? This is a path. It begins and ends at this point. So when you lift it into the cover, the lifted path, it will begin at x0, but the point at which it ends at is not necessarily x0 again. It's not necessarily a closed path. There's going to be something else, x1. Now, because x0 and x1 are in the fiber over this point, it means by definition, they are related to each other by a group automorphism. So there's a translation that will carry one into the other. And there's a unique automorphism that will do that for you. I leave that for you to think about why it has to be unique. It's not hard. Again, it basically has to do with the fact that you have bijections. So there's a unique automorphism that will send x0 to x1. And whatever automorphism that is, that's how you define alpha of this one. So this is how the way alpha is constructed. So now here's the part that you have to check. You have to check that alpha is indeed a homomorphism. That should not be difficult to check. You have to take two paths, f and g, multiply them together, and show that alpha of their product is the product of the alphas that you get. And now, for the sake of completeness, let's do it the other way around. Let's construct the map beta that will take a group automorphism and create a path, a closed path in the quotient. So let's remove all of this. And you can actually try doing this yourself. That there's what we call it's like the first map that comes to mind. So if you really get these definitions, which is really the more difficult part, then this is like the first map that comes to mind. This is like the natural thing to do. So let's remove this. So what do we have to do now? So to construct the beta map, so we have to take something in G, and then beta of G, whatever that is, well, it's something. And it has to be something in the fundamental group of the quotient. Okay, so here's how we do this. So since G, so what is G? This is an automorphism. G is an automorphism. So it's a homeomorphism of X into itself. So G is an automorphism. And thus, if you apply G to x0, right, so you have this x0. If you apply G to x0, you're going to get something new. Let's call it x1. And whatever that is, that's going to be an x. And x0 and x1, they're in the same mod class because one is the translate of the other. So they're in the same mod class. Now, take a path. Let's call this path F. And now this is going to be a path in the cover with f of 0 is equal to x0 and f of 1 is equal to x1. The reason why you can do that is because we assume that our spaces are path connected, as we've been doing up to this point. So you have 2 points, x0 and x1. These are 2 points in this space x. So there's a path between those points. So you take a path between those 2 points. And how do you get a loop in the quotient? You have to project it. You have to project it with the covering map. So then, if you project it, so that means you compose with the covering map. So there's 2 different pi's here. This is, of course, the pi. This is pi 1. That has nothing to do with a map. This is the quotient map. So then pi composed f would then be a map from the interval into your quotient space with pi of f at 0 being equal to x0 bar. So basically all you're doing is pi, I mean, if you want to, this is just, you can just say this is f bar. This is the same mapping as before, but it's being mapped not into x, it's just sending everything to the mod classes. But anyway, pi composed f at 0, so it's just x0, and pi of that's just a mod class of whatever that is. And pi composed f of 1 that would be x1 bar. But these are the same. So since x0 bar is equal to x1 bar, it means pi composed f is a closed loop in the quotient, and it's at the point x0 bar. So thus, we're going to define the beta map by taking an automorphism and assigning it to this class. So here's what you do. So let's just summarize this again. If you take an automorphism, you let that automorphism act on the base point x0. x0 will get translated to a new point, x1. And then you just take a path between those 2 points, x0 and x1. And if you would then project that mapping, you would get something in the quotient that will now be a map that will be a closed loop. It would be a closed loop now. And that's how this is being constructed. So your job is to check that these are inverses of each other. And once you do that, then you would have completed the proof that the fundamental group of the quotient is isomorphic to the group that was used to generate the quotient. And now we're going to look at a number of examples that will illustrate this theorem in action. The first example that we're going to look at would be the fundamental group of the circle. Our topological space would be the circle, and we need a base point to use because that's the way the definitions are set up. We always have a base point. y0, this would be 1, or if you prefer 1 plus 0i. We think of the circle in complex notation. The reason why we're calling the topological space y as opposed to x is because we're going to be using that previous theorem, that x would be a simply connected space, and we would quotient by something and end up getting the circle. Now, what we need to realize is that the circle is isomorphic to R mod G, where G, these are the group of integer translations. These are translations that look as follows, that they are automorphisms of the real line, and they take a point and they map it to x plus n. And as we've talked about, we have this isomorphism, and the isomorphism is actually quite simple, that if you have a point on the circle, which can be described as e to the 2 pi I theta, then you simply map that point to theta bar, where theta bar would be the translates of that point. So that would be theta, theta plus 1, theta minus 1, theta plus 2, theta minus 2, and so on. This is exactly theta mod G. These are all of the points on the real line that are equivalent to theta with respect to this group. So the translations of theta. And the reason why this is an isomorphism basically comes down to the fact that if you choose a different representative for theta, so if instead of using theta you replace this by theta plus 1, this will be replaced by theta plus 1, but theta plus 1 is in the same equivalence class. So in the quotient, that is the same space. And then we're going to use a fact which I think will be pretty believable, that the fundamental group of the circle at this base point would then be isomorphic as a group to the fundamental group of R take away G at the corresponding at the corresponding base point. So the way you get 1 is by setting theta is equal to 0. So this would be 0 bar, the class of 0 mod g. So this should be believable. It does require a proof that if you have homeomorphic spaces, then they have isomorphic groups, but that should be believable. Maybe we can put that as a homework problem. And now, here's what we're going to do next, is whatever this group is, it's isomorphic to G. That's our theorem, that the fundamental group of the quotient is isomorphic to the group of automorphisms that was used to obtain the quotient. And the group of integer translations is isomorphic with the integers. But we can do more than that. So what we can do is we can do more and even say what the generator class is. So the generator class would just, well, the integers have two generators. The integers, z is generated, so let's say we use +1, is generated by +1, because you have 1, 1 plus 1, and so on. And then you have the inverses, -1, -2, -3, and so on. And then you have the inverses. So every integer can be expressed as repeated additions of 1. So that's why we call it the generator for the group. And since the fundamental group of the circle is isomorphic to z, that means there's a generator class, and every other homotopy class will then be homotopic to certain iterations of that one generator class. Now to find it, we're going to use these isomorphisms. So here, the generator class is 1. Well, the generator class corresponds to translation by 1. Now, what is the corresponding homotopy class in here? So this is the map that this is the isomorphism between the group and the fundamental group that we had in the proof of the theorem. How do we get the isomorphism? Well, here's what we do. We choose the initial condition, so we choose something in the fiber, so let's say 0. And so 0 is an R, and so that's in our covering space. And then we're going to apply this automorphism to 0. So tau 1 of 0, that would be 0 plus 1, so that would be 1 in R. And what we do next is we're going to construct a path from 0 to 1 in the covering space. So the easiest path that you can pick, this is the path from 0, 1 into R, given by the formula that f of t is equal to t. Now, to get a path in the quotient, you simply compose it, you project. So to get a path in the quotient in R mod g, we project. So we would do pi composed f, and this would be a map from 0, 1 into the quotient. And this map would be given by, so it's t, but we would write t bar, because t bar, that just means it's the class of t. So here, let's just write it, so the corresponding path over here would be given by the formula just t bar. And now, to find the generator class, now I should say something very important. You should realize that we're using the covering. So we have a covering from the real line to the quotient. So we have this covering map. And we remarked that it is possible that you have a path in the covering space that is not a closed path, but when you project it, it becomes a closed path. So the projected path becomes a closed path. So this is now a closed path in the quotient because it starts at 0, it finishes at 1 bar, but 1 bar is 0 bar. So it finishes at the same point. And now you have to find the corresponding path that maps to this one. Well, this is the isomorphism. So if you want to get theta bar, then the correct object, the correct map that gets sent over, the correct path that gets sent over there is the path whose formula is e to the 2 pi I t. And that's what we've shown. So this is the loop, right? This is the loop that goes around one time around the circle. Okay, we can call this, for lack of a better name, I'm not sure what, I'm going to call it F again. I'm going to be sloppy. So that's the loop that goes counterclockwise, beginning at the point 1, one time around the circle. If you do it twice, So let's write it like this, f. If you do it twice, f squared, that's just juxtaposition. You're doing it twice. You're going once and then twice. So that would be the loop that goes around twice. And then if you do the inverse, the way you get the inverse loop is the reverse. So you just change the orientation. So that would be the one that goes clockwise, one time around the circle. And this way you end up generating the homotopy classes of the circle. And so what you're saying is that the fundamental group of the circle would then consist of the single point, that's the constant path, that's the identity. This is the one that goes one time around, and you have the one that goes two times around. In fact, I'm going to draw it like this. I'm going to draw it with two arrows because technically it's on top of itself, and so on. And then you have the ones that go in the opposite direction, and so on. And this corresponds to the integer. This is the number 0, this is the number 1, this is the number 2, 3, this is -1, and so on. They correspond to the integer. So it's nice that we have an isomorphism with the integers, but what is even nicer is the fact that we can explicitly describe how all of the homotopy classes look like. So we're not just saying that it's isomorphic to the integers, we're actually explicitly describing what all of them are. So this is going to be our first example, and now we're going to move to the next example. For the next example, we're going to calculate the fundamental group of the torus. So there's three ways of describing the torus. One of them, let's call this the concrete torus. This is the one that we visualize. So we have these three axes, and we take a circle and we spin it around like so, and we end up getting some kind of torus. We end up getting something like this. We end up getting a torus. The problem with the concrete torus is when it comes to doing mathematics on the torus, this is probably the worst way to describe a torus, because then you have to figure out the parametric equations. There's a lot of sines and cosines and all of that that goes into parametrizing a torus. And a lot of times that is not necessary. An alternative way to describe a torus is, let's call this the product torus. The product torus is, it's a product of two circles. Now this one you cannot visualize anymore because this is a complex number. So you have two real components and you have an additional two real components. So in total you have four real components. So if you wanted to visualize it, you would have to draw it as some kind of region in four-dimensional space, and then you would see the torus. So this is the reason why this approach is a little bit more abstract. However, it's easy to establish what the isomorphism is, because when you're located on the concrete torus, you can move around two ways. You can move around the inner ring, and then you can move around the outer ring. And you can maybe have theta. So if you have a point on the concrete torus, theta represents, let's say, the inner angle, and phi represents the outer angle. So theta would, so you pick some kind of orientation. It does not matter how you orient it. Theta will just tell you how many times you go around the inner ring, and phi tells you how many times you go around, let's say, the z-axis. So if I tell you what this angle is and that angle is, you would take the theta angle, you would spin around the inner ring the required number of times, by theta, I should say theta amount of degrees around the inner ring, and then afterwards you would then spin it around the z-axis the required number of times. And in fact, if you saw the parametrization for the concrete torus, it's in terms of two different angles which play this kind of a role. And then you can see why it's homeomorphic to a product of two circles, because you can describe any point. So you can sort of like map this to, let's say, well, a point on the circle is, I'm not going to use the same letters again, maybe use different letters. It's e to the I alpha. Maybe we can say 2 pi I alpha and e to the 2 pi I beta. So there's two angles that you have whenever you have a point on the circle. So that's, you have a pair of two angles, and that's basically what you have, and that's your homeomorphism between these two. And then the other way we can think of the torus is, as we've talked about, you can describe it as a quotient torus. So the quotient torus is, you take the real plane and you quotient out by g. What is g? G is the group that's generated by a horizontal translation and a vertical translation. So th, this is the translation map that takes a point xy and it sends it to x plus 1 comma y, and tv is the translation that adds plus 1 to the vertical direction. So these are the two translation maps that you have. And of course, you can talk about th composed with th. You do it twice. You can do th composed with tv, which is actually the same thing as tv composed with th. They happen to be commutative, and so on. And this group happens to be isomorphic to z times z. Maybe some of you have seen it written like this, z plus z. That if you're curious why you have different notation, is because if you have an infinite collection of groups, the direct sum has a different meaning than a direct product. But let's not go there because that's completely unnecessary for us. If you ever wondered, like, what's the difference between these two symbols? This is the direct sum, that's the direct product. When you have a finite amount of groups, they mean the same thing. They carry different interpretations when you have an infinite family, so that's where they change. But we do not really need to know that, so we're not even going to go there. So this is the quotient torus. So these are the two automorphisms that we're using. And we're going to calculate the fundamental group of the torus. And here's what we're going to do. We're going to use this to help us find the fundamental group. And then we will draw the picture on the concrete torus. And then we will be able to see how the generator classes look like. So there's two generators this time, horizontal translations and vertical translations. And then we will correspond to how that looks like in the picture on the concrete torus. So based on our theorem, the fundamental group of the torus, R2 take away G, and we need a base point, and the easiest base point to use is the mod class of the origin. This is going to be isomorphic with G. So that's the theorem, that the fundamental group of a quotient is isomorphic to the group that gave you the quotient. Okay, so let's say, so we have two generators. Let's find what these two generators are supposed to correspond. Since we have an isomorphism, these two generators have to correspond to two generators in the torus. So let's draw the picture of how they look like. So let's begin with the horizontal translation. So we start with 0, 0. That's our initial condition that we've chose in R2. And now if we apply the horizontal translation to that, we get 1, 0. So now we're going to pick a path in the covering space in R2 from 0, 0 to 1, 0. And the path that we can construct, the easiest one that we can use, this is simply the path f of t is equal to t, 0. So then if we compose it with the quotient map, we get a map from 0, 1 into the torus, into this quotient, and it's the map that simply takes, so pi composed f at t, that would be t, 0 bar. So that would be the closed path in the quotient. It's a closed path because 0, 0 and 1, 0, they're different in the covering space, but in the quotient, they're related to each other by a translation, so they become the same point in the quotient. So this is the reason why this is now a closed path. So, but what's the isomorphism? So let me do it over here. But we have an isomorphism that R2 mod G, not an isomorphism, a homeomorphism. There's a homeomorphism with the product torus. And the homeomorphism is quite simply that if you give me a point in the, if you give me a point in here, let's say I describe it as alpha comma beta as a pair of two real numbers. So it's really a class mod G, so it's a pair of two real numbers. I map that class to e to the 2 pi I alpha and e to the 2 pi I beta. So that's the way the isomorphism works, right? Because of course, if you replace alpha and beta by anything that's equivalent to it, you're just adding an integer to either alpha or beta, but because these are complex exponentials, they're periodic, and it's going to end up in the same point. So that's your isomorphism. So therefore, this path, t, 0, okay, so the path t, 0 corresponds to the path, let's say e to the 2 pi I t, and the other one you can say maybe just stays as e to the 0, which is just 1, right? That's just 1 in the product torus. Okay, and what path does that correspond to on the concrete torus? So on the concrete torus, this is the way you see it on the concrete torus. Let's say this is the inner angle and that's the outer angle. So the inner angle, notice it travels from 0 to 2 pi. So as t moves from 0 to 1, the angle travels from 0 to 2 pi, whereas the outer angle, it never moves. It stays the same. So you're only traveling along the inner ring. So this will therefore give you that class. So that would be a homotopy class. Homotopy class in the torus, in the concrete torus, the way we usually draw it. And without any surprise, the other generator, if you were to do the process, if you were to do this carefully for the other generator, so this is what we did with the horizontal generator, right? So again, let me just say this again. The fundamental group is isomorphic to G. G is isomorphic to two copies of Z. So one of them is the horizontal translation, one of them is the vertical translation. Those are the two generators for the group of automorphisms. If we use the horizontal generator, this process gives us this picture. If you were to do the same thing with the other generator for G, TV, it would basically be the same thing, but you would sort of like interchange the roles of those two, and then you will get the outer path, and this would be the other homotopy class. And these two classes, right? These two classes completely generate all homotopy classes on the torus. So everything is made out of these two. And the interesting thing about these, to further add, I know we talked about this previously, but I want to talk about this again because it's important. So if you call this loop F and you call this loop G, they satisfy the relationship that if you look at the homotopy class of F and you look at the homotopy class of G, then they're actually commutative. It has to be because the group is a commutative group. But what I want to show you is I want to actually draw a picture for you so you get to see that this relationship is true from a picture. What makes this surprising is because F by itself and G by itself, they're different homotopy classes. You cannot turn this one to that one by some kind of deformation, like some kind of way of deforming the path to make it look like that. However, it's interesting that if you do F first and then G, and then you do G followed by F, that gives you the same thing. So what we're saying is, if you were to go around, let's say, one of them first, and then you go around the inner one, you can homotope that, right? You can homotope that picture so that the blue one is the one that now goes around, and the red one is the one that goes on the inner one. And that's what we're saying. And this is rather surprising that individually you cannot interchange the blue one with the red one, but somehow if they're together, you can do it. And the explanation here has to do with the fact that if you have a single loop, you're not allowed to break it open. This is not allowed. Because a homotopy has to keep the base point fixed. So you're not allowed to do that. However, if you have two loops coming together, so if you have, let's say, some kind of loop like this, and you have another loop like that, you can now open them up for the simple reason because it stays as a closed path. And you basically open them up, you move them around in a certain clever way, and you rearrange them so that you interchange them. Now, I gave you a video animation from before, but I think this is another way you can see it. As we've said before, you can think of the torus as a square where the opposite edges are glued together and the vertical edges are being glued together. And if you glue this, you end up getting a torus. So here's the way you can see what's going on. If you draw a path like this, notice that the endpoints, they get glued together. So this red path on a torus is going to be a closed loop. And if you have a path going across, that's going to be another closed loop. Now here's the homotopy process. Imagine you take the point where they come to, where the red and the blue one come together, and you start pushing it upward. So if you do that, you would end up with something like this, and then this. And if you do that again, you end up with this, and then that. If you just do that a bit more, you end up with this, followed by that. Maybe you can exaggerate it just a little bit more. And then the homotopy will finish where the red one is up here and the blue one is on that side. But because this is a torus, the upper piece corresponds to the lower piece. So you can redraw this where the red one is now at the bottom and the blue one is on the left. And look at what you've done. You've constructed a homotopy that take these two edges, which are technically closed loops in the torus, and you came up with a homotopy that put them together. And this homotopy illustrates what we were saying, that you are allowed to open up the blue path, like individually. The red one, you see, the red one by itself cannot be moved to the vertical position. You're not allowed to do that, because the point where the red one stops, that will not make it a closed loop anymore, because the point here and the point there do not come together. But because you have two edges like this, because it continues through, the endpoints never move. And so this is what happens. So it's just very interesting that the fundamental group of the torus is an abelian group. That is something that might be surprising at first, but that's what the math shows us, and now that's what the pictures shows us as well. Our next example will involve the projective plane. Let's recall the projective plane. We start with the unit sphere, two-dimensional sphere, and G will consist of two automorphisms, the identity and the antipodal map, where the antipodal map is the map that sends a point on the sphere to its negative. And then the projective plane is defined to be the quotient of the sphere by the group of automorphisms. So to give you an example, one of the elements in the projective plane would look as follows. Let's say we have the north pole, 0, 0, 1, and 0, 0, 1 would then be equivalent to its antipodal point, 0, 0, negative 1. So the north and south pole are being put into the same equivalence class. So this entire pair is a point. So it's a little bit confusing because it's not one point, but it's really 2 points, but they get put together into a set, and the whole thing is now a point. And then you can represent this as 0, 0, 1 bar, right? It's the mod class of that. Or you can represent this as 0, 0, negative 1 and the mod class of that. So that would just be 1 point. And then you have many, many other points, but you always have 2 in each mod class. So because of this, the quotient map from S2 to P2 is what we call a double cover. Double cover. You can also call this a two-sheeted cover. So the number 2 just indicates how many pre-images you have in a point when you pull it back. So this entire point is really 2 points put together. So when you pull them back, you get 2 pre-images on the sphere. Now, here's the way we visualize. Well, before we do that, let's just say what the fundamental group is. So thus, the fundamental group of the projective plane at a certain point, let's say at the point at the north pole, 0, 0, 1, that would then be the fundamental group. So it's not even isomorphic, it's actually equal to that, because the projective plane by definition is the quotient. It would be S2 mod G at 0, 0, 1. And this is isomorphic to G, and G contains 2 automorphisms. The antipodal one satisfies the property that if you compose it twice, you get the identity, because the negative of the negative would be itself. So this group, it's the group of 2 elements. So this is Z mod 2. So that's what it is as a group. But I want to do a little bit better, and let's actually describe visually what the 2 homotopy classes are in the projective plane. So according to this result, there's supposed to be 2 of them. So let's actually say how they look like. So one of them is, of course, going to be the identity class, which is the one that sits at the point at the north pole. So that one is not interesting. It's the other one which is more interesting. So here's the way we do it. We're going to use the isomorphism from the group to the fundamental group, exactly as we did in the other examples. You're going to pick something in the group. In this case, we're going to pick the antipodal map, and we want to find the corresponding loop in the projective plane. The way we do that is we take our initial condition, which we decided to use as 0, 0, 1. This is an S2, and we're going to apply the antipodal map to that point getting 0, 0, -1, also on S2. And now we're going to construct a path from 0, 0, 1 to 0, 0, -1. And it does not matter how you construct the path, because whatever you get, they will all be homotopic to each other. So you have the North Pole, you have the South Pole, and you can like imagine perhaps that this is the path that goes like that. Okay, so that is the path. And then this path, let's call it F. Okay, so this path, how does it look like in the projective plane? Well, here's how we often like to think of the projective plane. Because in the projective plane, the northern half and the southern half, they're being identified together. So there's no need for you to draw the lower hemisphere. And the points that are on the equator are being identified together across the diameter. So they're just being identified across. And the way we like to visualize the projective plane is take this northern hemisphere and push it down. Push it down so it turns into a disk. So you have a disk, and then the points in the upper half of the disk on the boundary correspond to the opposite side on the lower half of the boundary. And the way we visualize the projective plane is gluing the upper half with the lower half, but we have to glue it with a twist. If the folding took place vertically, then the upper half and the lower half, they will fold together perfectly, and you would end up getting something that was topologically a sphere again. But here, before you have to twist, you have to sort of take the lower half, twist it before you glue it, so things get matched the correct way, and that's how you get that like twist in the sphere. So it basically looks like a twisted sphere. Technically, you cannot draw it without self-intersections because it's something that does not embed in three-dimensional space, but that's really the best you can do. And in this kind of a picture, when you flatten it out like this, so when you flatten it out, note what's going to happen with the equator. With the North Pole. The North Pole gets pressed down, and when you press it down, it becomes the center. So in this picture, that's the center. And the path that we have, this is the path that goes like this. So the path in the quotient would be a closed loop, because these 2 points, they come together in the quotient, and you end up getting a closed loop in the projective plane, which would be the other homotopy class, the non-trivial homotopy class. So to see what it is, we go like this, right? We go like this. So in our picture, we start in the North Pole, and we kind of go like that. So we kind of go out to the boundary. I'll draw it at an angle so it's a little bit easier to see. So you kind of go out to the boundary like this. And when you get to the boundary, because of the equivalence, continuing down here, that's the same thing as jumping over to the other side and then traveling back to the North Pole, because this lower half is redundant. So you kind of travel back to the other, and you kind of go back. So in the picture, you get on the other side, and you travel back to the North Pole. So that is how your path would look like. And so we can now visually describe. So now let us visually describe the homotopy classes of P2. So there's going to be 2 of them, because it's a group of 2 elements. So one of them is the identity element, which is the one that just stays at the North Pole. That one is not interesting. But the other one is a little bit more interesting. This is the one that it starts in the North Pole, it goes like this, and then it continues across on the other side. By the way, just so that we understand this, if you drew it like this, let's say, that's the exact same thing, because you can just imagine that you take this and you sort of spin it, you homotope it into that position. So this is just one representative for the homotopy class, but they all sort of look like that. So there's 2 of them. So let's call this one F. So since the fundamental group of the projective plane at that point is isomorphic to Z mod 2Z, it means that if you take this homotopy class and you square it, so you do it twice, it should give you the identity class. It should be homotopic to the identity homotopic class, because you're working with integers mod 2. If you add something twice, you get the identity. So let's visualize. So let's confirm this in a visual way. It has to be true, because that's what the algebra shows us. But let's confirm this in a rigorous way. So here's how we would confirm this. So if you do it twice, So if you do F juxtapose F, this is how it looks like. You have this is F once, and then you're going to do it again. So you I'm going to use a different color, and then you're going to go over it. It really has to be on top of itself. And now here's what we're going to do. We can homotope the blue one, keep the red one as it is, and start spinning around the blue one, and you're going to see the homotopy. So you have your circle, you have your North Pole, you have this one going like that, and if you spin a blue one a little bit, it's now going to go like this. And you can spin it a little bit more. So you can spin it a little bit more, and spin it even more. So basically we're constructing a visual homotopy. Let's kind of spin it a little bit more. Let's say we go like this, and spin it even more, and eventually you get to a position where it just goes backwards. And then that picture would represent F juxtapose the reverse path, right? So F juxtapose F is homotopic to F juxtapose the reverse path, and when you juxtapose a path with its reverse, that's just homotopic to the constant path that stays at the North Pole. And this is sort of the visualization for the homotopy, and that justifies why the fundamental group has to be the integers mod 2. So it's interesting because at first you would never think of a path that if you transverse twice, it becomes the identity, it homotopes to the identity, but the math forces that conclusion on you. And then once you know that it has to be like that, then you can search for that kind of property in the picture. Now, there is one part here that we have to address, and it's this. So when we're using this isomorphism theorem that says that the fundamental group of the quotient is isomorphic to the group of automorphisms, there's the assumption that the covering space is simply connected. So the question here is, why is S2 simply connected? And what I'm going to do is, I'm going to give you, on the homework, I'm going to give you a fake proof. So a fake proof is a proof that looks correct, but there's going to be a small little technical detail that messes it up. And I'm not going to tell you what it is. It's an interesting proof. It's going to show you why S2 is simply connected. And then you have to spot the mistake. And to fix the mistake, so it is possible to fix the mistake. I'm not going to tell you what the mistake is, but it is possible to fix the proof. But it turns into analysis. So you have to use certain facts from analysis to do that, which is not part of the class. So that's why we're not really going to show that proof, but it's just something interesting to see. And I want to finish with, I'm going to give you some problems with the Klein bottle as well, so you get to experiment with that. But what I wanted to finish with is this method of computing fundamental groups is limited. It's a limited method because if you want to find the fundamental group of a space y at some point y0, you need to find a simply connected space X and a group of automorphisms that acts evenly on X so that Y is homeomorphic to that quotient. And in general, this could be difficult to find. So it is a nice method, but this is what we were saying. It is a limited method. Sometimes it works, but in many cases, it's not going to be appropriate because you're trying to find a way of how you can describe the topological space in which you're interested in as a certain quotient. And sometimes that's not easy to do. But assuming you could do it, then you have this nice theorem that connects the fundamental group of the quotient with the group of automorphisms, and not only does it tell you it's isomorphic with G, but you can actually draw the homotopy classes in your space. You can actually show what they are that generate them, or show how all of them look like. So it's a nice method, but it is limited, of course. And the reason why we're showing this method for computing fundamental groups is because we're not particularly that interested in the fundamental group in this course. We are more interested in covering spaces, because covering spaces are important throughout mathematics, and you will probably see them again in the future. And the point of this course is one of the goals of this course is to make you comfortable with covering spaces. So if you see them again, you have prior experience. And this is one of the uses that covering spaces can be used for. They can be used for many other things, but this is just one of their uses. And it felt a nice illustration of the techniques of covering spaces.